Hello everyone. Today we'll be presenting our ETD 555 final project, temperature activated fan control system. Our group members, me, myself, Dishang Patel, and we are total three members in the group. The other two members are Hemi Patel and Bhargav Mori. So, we are total three members, and we have done this project under the supervision of Professor Dr. Rakesh Kantaria. So let's begin. So this is the outline for our project. In this presentation, we will cover the problem statement, design requirements, the system overview, hardware design, software control, LabJack program, uh, the isolation and motor driver details, prototype and testing challenges, and the final conclusion. So, problem statement. First of all, many small electronic devices can overheat if the cooling system is not controlled properly. So, if the runs all the time, it wastes energy, and if people forgot to turn it off, overheating can damage components. So our main goal was to build a fully automatic fan control system that monitors the temperature and turns on the fan above like set threshold, like which we have set in the our program, and turns it off when cooled down. So like when the temperature goes back to normal, the fan automatically turns off. And also which includes safety features like an emergency stop button and the emergency terminate button. So like emergency stop terminate button will directly kill the program, and the reset button will completely reset the program. Yeah, next slide, which is design requirements. The mandatory requirements were interface the system to a PC using LabJack U3 or UE9, control a 12 volt DC fan, which provide optical isolation to protect the LabJack. We also use an H-bridge driver for the motor and include the emergency stop button and the reset button as well. So these were the core targets of our design which were needed to be met. So our system overview. So here's the system overview. A PC runs on our program using the LabJack UD driver. So through the USB, yeah. The LabJack communicates with our circuit. The LabJack reads the temperature, which was the device called LM35 sensor, and the emergency reset button, which resets the program, and the emergency stop button which terminates the program. And it outputs a digital control signal on through FiO4 to turn on the motor and turn it off. So that signal passes through the 4 and 2 opto isolator uh, through the H-bridge driver. Okay. Next slide is.
Thank you, Dishank. So now my name is Bhargav and I will continue the rest. So our temperature sensor is an LM35. It outputs 10 millivolts per degree Celsius, which gives a very linear response. This connects to an AIN0. On the LabJack, we also added emergency and reset push buttons. When pressed, they pull the voltage below 1 volt, allowing the LabJack to detect them and take actions. This gives us safe and simple user control. So On this slide, we will talk about hardware, how isolation and motor driver works. So to protect the LabJack from 12-volt motor side, we use an 4N25 opto-isolator. This separates the two ground system and blocks noise or voltage spikes. The edge bridge, which is L293D driver, handles the actual motor load. It supports up to 600 milliamps and it includes internal clamp diodes for inductive loads. In our project, we only needed one direction, so we used it mainly as an on or off motor driver. The fan is a standard 12-volt DC motor. So, our design mainly focuses heavily on electrical isolation. The 4N25 opto-isolator ensures the lab jack stays completely protected from any EMF, noise, or spike generated by the fan motor. This is important because USB devices can reset or disconnect if noise enters the ground lines. We selected resistor values to achieve clean switching into the L293D. We also kept the LM35 along wiring separate, uh, LM35 analog wiring separate from motor wires to avoid interference. So the DC motor behaves as an inductive load, meaning it produces voltage spikes when switching. The two the L293D's internal clamps diodes help absorb these spikes and protect the motor driver. Motor startup current is higher than running current, but still safely within the LN, LN L293D's peak rating. There is a small voltage drop across the L293D, which slightly reduces speed, but it is acceptable for cooling applications. So next in this slide we will talk about how control behavior and threshold response works in LM35. The LM35 provides a clean linear temperature signal. When the sensor heats up past about 27 degrees Celsius, our system activates the fan. Due to thermal inertia, the temperature drops gradually, preventing rapid on or off flicker. There is also a neutral hypersonic system which smooths the transition. The threshold was chosen based on typical safe operating temperatures for electronics.
Thank you, Bhargav. Now I will be continue from here for the next slides. Next, the topic is power management, protection, and safety features. For safety and reliability, we separated the power sources. The lab jack is powered from USB, which provides a clean and stable 5 volt, but the motor needs 12 volt and motor draws a lot of current when starting. If both share the same power, the lab jack could crash or disconnect, so we used a completely separate 12 volt power supply for the motor. This prevents brownout issues and protects the lab jack. We added two safety switches: emergency stop, which instantly cuts the signal so the motor stops immediately, and the reset button, which restarts the system without unplugging anything. We also used screw terminals, thicker wires, and proper grounding to make sure the circuit stays stable even when the motor is vibrating. All these safety features ensure that our system is reliable and protected during a long-term use. Next. Our next slide is about key design decisions and alternatives. While building this project, we had many design choices. For driving the motor, we selected the L293D H bridge instead of building our own transistor circuit. This chip already has internal protection diodes, supports higher current, and saves lot of wiring time. Using it made the system more reliable and easier to debug. We also used a 4N25 optocoupler between the lab jack and motor driver. This protects the lab jack from motor noise and from any possible short circuit on the 12 volt side. Because the lab jack is a USB device, isolation is extremely important. For motor control, we kept the design simple with an on or off control instead of PWM speed control. The goal was stability, not complexity. And finally, we started with a breadboard prototype and later moved to a PCB. The PCB version reduced noise, improved connections, and made everything mechanical stronger. The reliability testing and validation. To verify that the system was working properly, we performed several reliability tests. We tested the temperature sensor response at different room conditions and confirmed that the fan always turned on exactly at our threshold. We also checked the emergency and reset buttons multiple times to make sure they respond correctly and instantly. The isolation using the 4x5 was tested by running the motor repeatedly. Even with sudden startups and electrical noise from the motor, the lab jack stayed stable without disconnecting from USB. The motor driver did not overheat, and the voltage drop across the L293D was acceptable for our cooling application. Overall, all tests showed that the system was safe, stable, and reliable even without continuous running. And then the final conclusion slide. So to conclude, our project successfully created a fully working automatic temperature controlled fan system. We met all the design requirements: accurate temperature sensing, automatic fan deviation, emergency stop and reset features, isolation between lab jack and the motor, stable 12-volt motor control using the L293D. The system reacted smoothly to temperature changes and worked safely without damaging any component. Looking forward, we can add improvements like PWM speed control, LCD display, Bluetooth monitoring, adjustable temperature threshold, faster sampling and data logging. But even in its current form, the system is dependable and practical for real-world cooling tasks. And thank you for listening. Now this are the references that we used in our project. Thank you, and this was our end of the presentation. Now we will demonstrate our working project demo. Thank you.
Hi, I'm Bhargav Mori.
I'm Hemi Patel.
And I'm Dishank Patel, and we'll be presenting our ETD final project today. So this is our circuit, and this is the temperature sensor, this is optocoupler, this is S-bridge driver L293D, and these are two push buttons. One for reset button, which restarts the program, and one is an emergency stop button, which terminates the program when we press this button. And this is the motor, which turns up the fan.
Which turns up when the temperature goes out to threshold, which is 27 degrees, which we have set it in this program. And you can see as I start the program, the temperature is right now 21.38, and as you can see, I'm transferring the heat from my body to temperature sensor, and it's rising the temperature. And when it goes up to 27, the motor will start working. As you can see, there is 27 and the motor is turned on. And if I release my fingers from the temperature sensor, and when the temperature goes off, the motor is turned off, as you can see. And now I will test the reset button, which is AIN2. So as you can see, as soon as I press the AIN2, it's 0.0, 0.01, and the motor is off. The system is restarted. And now we will test the emergency push button. And as soon as I press the emergency push button, you can see the program is terminated. Thank you.
And that's our project, and thank you for watching.